Okay, so we'll continue our afternoon session today. Our two afternoon speakers have very graciously agreed to give up a little bit of their time to somebody whose talk was canceled yesterday because of the weather. So we'll hear for about 45 minutes from Professor Hou, who's going to talk to us about density Corradi Hajnal theorem. I think I pronounced the name wrong, but anyway. And then we'll have a speaker from yesterday, talks about 45 minutes, and then the last speaker will talk for the last 45 minutes. So if anybody needs to take a break during one of the lectures, I think none of them are going to complain at you because we don't have any extra time really. So we'll just go ahead like that. So 45 minutes, we'll turn the time over to you. So let's welcome our speaker.
Thank you. Thank you for the introduction. First, I'd like to thank the committee giving me the opportunity to give the talk. Today, I want to talk about different type problems of the degenerate hypergraphs. It's a joint work with Dr. Xiji Liu and my 4 students. I want to divide my talk into the 3 sections. Firstly, I think we need some notations. Okay. First, is a R graph. R graph is a collection of the R subset of some founding set V. V is a vertex set of H, and the R subset is called the H. It's called H of H. Given 2 graphs, 2 R graphs, this one F and H, we use the mu FH denote the maximum number of vertex-disjoint copies of F in H. And this one, we call this F matching number of H. Well, when F is an H, this one is simply just the matching number of F of H. Okay. Next one, I should talk something about term members. For the graph F, we see another graph F is a F-free if the H doesn't contain any subgraph isolated to F. And the term member of F denoted by EX. NF is the maximum number of edges in F-free R graph on inverses. Another notation is about term density, denoted by pi F, is the limitations of the EX NF over N choose R, when the N is 10 to the infinity. Actually, pi F denotes the main term of the term member and the R graph is called a degenerate if the pi F is 0. Otherwise, we call it a no degenerate. Okay, I think the study of the term member of the given graph, a given R graph F, is perhaps the certain topics in extremal graph theories and extremal half-graph theory. Much is known when R equals 2, which means that F is a general graph we just talked about. And the classical theorem shows that the complete graph K of on L plus 1 versus the term member of the complete graph on L plus 1 problems is uniquely achieved by the complete L-partited graph on inverses. This graph we call the term graph. When R it's at least when R equals 2 for the general F. For the general F, we know that the celebrated Eddington Stenois theorem shows that this one, the term member of the general graph F is not far from the term graph, which means that we can determine the term density of F exactly when F is a graph. However, when For hypergraphs, I mean that R is at least 3, demanding the turn density of S is known to be hard in general. For example, just consider the complete R graph on L versus. Demanded the turn cities of this graph, of the complete R graph on L versus is still wide open. Even for L equals 4, we didn't know the best possible or best answer about this one. Another topic is a degenerate case. A theorem of the Erdős shows that a R graph is degenerate if and only if F is the R partit. I mean that the vertex set of F can be partitioned into R parts such that each edge contains exactly one vertex from each part. However, determining the growth rate of the EX in F for degenerate graph is a central and difficult topic in extremal comptonics and remains open for most families. Even for F, even F is a graph, a simple graph. For example, even cycle, these problems is still widely open. For example, another famous problems in this topic is even cycle problems, which ask for to determine the exponent of the even cycle, the term number of the even cycle. However, it's remain open. These problems is only solved when k is in 2, 3, 5. This means that they only know the C4, C6, the C10, exactly the exponent of its term number. For other cases, we even didn't know the exponent. Okay. In this case, we are interested in the density constraint that force the R graph to have a large aforementioned numbers. All the term members, we just show that there exists the one special graph. However, we want to find many vertex-disjoint F. This is motivated from the Erdős-Galat theorem. We show that if F is an H, R equals 2, we mean that it's a graph. It's a graph, we mean that we want to find a matching in a graph G. Erdős-Galat theorem tells us that if the number of edges in G is at least this one, then we can find a match. We can find a match of size at least t plus 1. This one is a two extreme graph. The first one is a complete graph of order 2k, 2t plus 1, and the other one is a complete graph on n versus minus a complete graph on n minus t. However, we exactly extend the naturally we can extend the Erdős-Galat theorem to R graph for R equals 3. These problems we have the similar conjecture posed by Erdős. However, these problems, although there are many results on this topic, but this problem is still open now. Actually, for general F, there are few results about this one. We mean the TF denote the T vertex disjoint copy of F. We want to demand the term member of TF. Okay, before we list some results, we first give examples. We give two graphs, G and H. The vertex of G and H are vertex disjoint. Now we define the joint of G and H. We use this symbol to denote the joint of G and H is to be another R graph obtained from the union of the G and H by adding all R sets that have no intersection with both Vt and Vh. I mean that when G and H are graphs, the joint of G and H, we mean that this is graph G and this is our graph H. We connected each vertex, connected all the vertex from the G and H. We mean that G and H is a complete bipartite graph. Okay. For non-degenerate case, others first studied these problems and show that the T plus one K3, the triangles, the triangles is about this one. And the extreme graph is about KT, the union of the KT and the triangle graph. Okay. We remark that we not only just know the triangle, we also know the extreme graphs. And we remark that the T is something, is a parameter, it's not a constant. It's a parameter, it's related to n, it's a square root of n. These problems have been improved to Moon for T and extends to all complete graphs. He showed that if T is not larger than n from a small constant epsilon, then the extremal graph of the T plus one, the extremal graph of the T plus one and of the cliques on L plus one vertices is just this graph. It's the union of the complete graph of on T vertices and the triangle graph. Recently, for non-degenerate graph F, we have studied his triangles asymptotically. In our paper, we show that if the non-degenerate half graph satisfies some properties, we mean the smallness and the boundness, then for any T, it's at most the n, where epsilon is a constant, depend only on F. We always has his triangle his extreme graph. It's just like the complete graph and the joint of the complete graph and the extreme graph. Okay. Now we want to talk about how about a degenerate case. Before that, I need some definitions. First, let F be a R graph and S be an integer. We use this one. Fs denote the collection of the induced graph on n vertices, on S vertices. This is a collection of the sum graph, induced sum graph of F on S vertices. Another definition is about a common number of F, denote the tall F, is a minimum number of vertices such that each edges contain at least one vertex in S. It's a tall F. Okay. Then we give three graphs, three special graphs. The first graph is a joint of the complete graph on T vertices and the extreme graph, the extreme graph of F. Just the extreme graph in this one. In this one. The second graph is also a joint of the complete graph, but the order is this one. the joint of another extremal graph. This extremal graph is not the f, but f m minus tau plus 1. And this one. Okay, we can show an example. When f is a cycle, is a full cycle, is a cycle of length 4, we mean that m equals 2, tau equals 2, m equals 4, tau equals 2. Now, this one is f3. We mean that 3 verses just a path, just a path of length 2. Okay, so for cycles, this one is a sparse. I mean that the extremal graph about f3 is sparse. It's just only the disjoint edges. Okay. The last graph is just the union of the complete graph and some extremal graph of f. For this C graph, we want to choose the C edges of each graph. We use the GI-NTF denote the number of edges in the GI-NTF. It's easy to see that the true number of T plus 1F is at least GI. And I mean that the graph we just constructed is a lone bound. Okay. Our main contradiction is that we think that when T is in this one, T in this one is from 1 to something like this. Something like this. We want to show that G1 is asymptotically optimal for the T plus 1 of F, the term number of the T plus 1 of F. When T equals to lying in this interval, it's a jump from this one to n from some small constant interval, which shows that G2 is asymptotically optimal. And similarly, the G3 is in here. It's in G here. I think that one of the motivation about these problems is Hajnal problems. Hajnal problems tell us that if the minimum degree of the graph is at least this one, then we can find T plus 1 vertex-disjoint triangles. Especially when the minimum degree at least 2n/3, they contain a cosine factor. We mean that the vertex set of the G can be partitioned into the vertex set of the triangles. Okay, now we state our problems. We state our result precisely. At first, we give the definition called the boundings. A boundings is something like this: that C1, C2 be two real number, and our graph F is called C1, C2 bounded. If the following hold, that for large n, such that every n versus R graph F, R graph R, H with the maximum degree, the delta H denote the maximum degree is at least C1 times n minus 1 choose R minus 1. And the number of edges is at least 1 minus T2 times EXNF. We mean that if the such graph has a large maximum degree and a large number of edges, then we show that F contains H contains a copy of F. And we see F is bounded if it's C1, C2 bounded for some C1, C2. Okay, What does this mean? This means that if R graph H is F-free, doesn't contain F as a subgraph, and it has a vertex of degree of the large degree. I mean that it has a vertex of the degree at least this one. Then we can show that the number of edges is not this one. This means that the extremal graph of the F have the small maximum degree. I mean that they almost the regular. We can remark that many well-studied degenerate half-graphs are bounded. We can just give an example. First is for no forest bipartite graph that became a tree after removal of vertices. I mean that if a bipartite graph, we know that for graphs is a degenerate if and only if it's bipartite. If we can remove the vertex such that the removing of text results in a graph, results in a tree, this graph is bounded. For example, even cycle is bounded. And the bipartite theta graphs. Another one is a complete bipartite graph TST. However, we need T at least something like this. And the 2 by 2 grid is also bounded. Another one is the expansion of the complete graph, or the complete bipartite graph as T. When here we need S at least 4, and the T is something like this. The expansion of the complete bipartite graph, we mean that for each edge we insert a vertex in each edge such that all the new vertex are different. Okay, for the first interval, our first result is about this one. If F is C1, C2 bounded, where C1 is not at most M1 over M, this is important in our proof. Then for safety large N, we always have the extremal construction of the T plus 1F is a union of the complete graph and the extremal is a extreme construction. Here we need the T is at most this one. Delta is something like this. It's a constant depending only on C1, C2, and F. Okay. This is our first result. There is an interesting inquiry for our result. Okay. First, we give a definition about substitutions. Let F be an R minus 1 graph. The substitution of F is a R graph denoted as we adding a new vertex in F, and all the edges containing the edges in F and the new vertex V. I mean that we give a central vertex and all the edges containing V. This one. These are called substitutions of F. It's easy to see that F is bounded. It's C1, the 1 bounded. C2 means that 1. But we always have C1 is the term density of F. Okay. So since it's bounded, so we have this one. If the term density of F is at most advanced 1 over M, so we always has his term density. We always have the extremal graph of the substitution of F. Okay. There is another interesting corollary. I mean that this one. We know that the most important result is the triangle in graphs. However, in hypergraphs, what about how to define the triangle? There is a generalized triangle TR in hypergraph. I mean that R graph. This is a generalized triangle. It's a graph. It's an I graph with 2R minus 1 vertices and 3 edges. The first one is 1, 2, 2R, 1, 2, R minus 1, R minus 2, and last edge is R plus 1, 2R minus 1. Okay. This is a generalized triangle. Okay, study the triangle density had a long history. As far as we know, we just demanded TR for R is at most 6. I mean that the pi CRs remain undemanded for all R is at least 4, at least 7. But demanding the sufficiency of TR, demanding the transition of sufficiency of TR may be a more challenge in general. For example, just for T3. A T3 just means a triangle, just means a triangle in a graph. The sufficient of T3 is K43 minus. It's K43 minus. Denote the complete 3 graph on 4 vertices minus I edges. By deleting I edges. The density of this graph is remain open. Just a sufficiency of T3. Okay, our result has a sufficiency. We don't know his density. So we don't know his extremal graphs, but we know T plus 1, the sufficient of TR's extremal graph. Extremal graph is just the union of the complete graph and this extremal graph. So I think this result is interesting for us. For the second interval, we have this result. We have this result. We don't know the exactly the extreme exactly the term number of this one, but we have the upper bound, and the upper bound is something like this. It's something like this. Okay, we always have P is at least this one, and at most this one. This is called in our middle interval. Okay, this is this one. B is a R-parted R graph. R-parted R graph. For R equals 2. For R equals 2, we can get better. We can get better. It means that if B is a bipartite connected graph, and its current number is S1, is S1. We always we need use this one. The current number is current number. Is the number of verses in one part, in the small part. Okay. We know it's term number. We know this is term number, but we don't know his extremal graphs. We don't know his extremal graphs for the interval. And always T sentence for something like this. This one is the square root of n, and this one is something, the minimum is here. This is constant. And the upper bound is something about epsilon. We think that this one is not important. It's important from here. Okay. More especially, if the B is a complete bipartite subgraph, we can do better, which means that this one we can delete this one. So we have the its extremal, its actual member is something like this one. And we always have t from the maximum in here. And the upper bound is something like so on. Okay. For the last interval, we need a new definition called M star. We call n versus R graph H is a M star for some M is not at most n if that there exists a vertex set of H V1 of size M such that every edges in H contains at least one vertex in V1. I mean that M star, we mean that the common number of H is at most M. Okay. Use this one, we can define another term member called the star term member of F. Okay, we give the example. We use this one. The star M N F denote the maximum number of edges in a F-free R graph M star on with n vertices. We just related our graph into the M star graph. It's easy to see that this member is at most the term member of F. Okay, if we have this one, we can determine the complete R-parted R graphs. The M star, this one has the upper bound on this one. Has upper bound on this one. This problem is easy to get using the Erdős arguments. So for the last interval, we have this one. If B is an R-parted R graph, we know that the upper bound of its term members is at most something like this. And we always have T, we know that T is at most N over S. And N over S minus something like, I'm sorry. Okay, we don't know the exactly bound, this one. But we can give an upper bound. Even for B is a for cycle, we don't know the extremal bound, which is okay. For graphs, we can have the better bound. Also, the upper bound for the T plus N 1B. It's also the upper bound, and this one we can do the better. Then I think give some conclusion remarks. In this section, we just give the all the T plus 1 vertex-disjoint member of the external member. We always have the vertex-disjoint graph are the same. However, when the graphs are not the same, we mean that you can demand the F1, F2, Ft plus 1. You can always ask this one. This one denote the maximum number of edges in an inverses R graph without pairwise vertex-disjoint copies of F1, F2, and then F2, Ft plus 1. Our method could use one could use a similar proofs for this problem. For use these problems. Okay. Another one is this one. We want to the following nature problems is that we want to demand all the for all the t, and demanding the term member of t plus 1 for C4. Actually, for all the t, the only demanded graph is a triangle. So we think that this one is interesting us. Especially, we just know the first interval, we have the extremal graph. The second interval, we don't know extremal graph, but we have the extremal term member. In the last interval, we didn't know the extremal term member. Okay, these problems is interesting. And the simple one. As we have given the three graphs, the G3 is not maximal. In fact, you can construct it more graph with more edges than G3, which has not t plus 1 vertex-disjoint of C4. But the number of edges is closely related to this one. Okay. However, we don't know the extremal graph. What is the extremal graph? This is because that we didn't know the indeterminate number of the extremal graph of C4, which I mean that we don't know the extremal graph of C4. So I think that the following problems is interesting, and that if you know the C4 free graph, if you know the indeterminate number of the C4 free graph, do you know what's the maximum number of edges? I mean that, do you know the maximum number, what's the maximum number of edges in the C4 free graph with the indeterminate number? Indeterminate number is at most alpha. Alpha is a constant, or maybe is related to n. I think that it's just the square root of n. Okay. Another question is that in our second interval, in the middle interval, we always have this one. The lower bound is about a maximum of this one, and another one is a square root of the extremal graph, the term members minus n to r minus 1. The last bound is asymptotically tight. However, this bound is not asymptotically tight. So I think that the problems is characterize the family of bipartite graph for which the lower bound, this one, can be omitted. Okay. Another problem is that for the first interval, we know that it is extremal graph, but we don't know exactly what about the SF. I mean that what the largest view of the SF, such that for all the t from 1 to this one, its term member is G1. Because in the first interval, we not only know its term member, we also know its extremal graphs. Okay, but we don't know about this one, SF. When F is a full cycle, we even didn't know how large about SF. We just know it's something about the square root of F. The last question is about the Corr rate of our first interval. It means the suspicion of F. A suspicion of F, we have the problems about this one, which means that we want to use in the term density. We always use the term density at most the 1 over the number of F. So from the 15th or necessary condition, for non-degenerate graph, something for this quality. Something for this one quality. Okay. We know that this one is at least this one. If the F is no degenerate case, problems of others show that pi F at least this one. So we want to this equality hold. We always need R is at least 4. As for R at least 2, this one doesn't hold for the non-degenerate case. This is all my talk. Thank you.
Take maybe a couple minutes for questions. Any questions?
For the generalized triangle, can you show the result? Can you show?
Okay.
Oh, so the condition is when R is at least 4, right? So it's
Yeah. This one.
Okay. It does not include the K43 minus.
No. As K43 doesn't contain this one, we want this one. It's neutral for K43 minus. Yeah.
Okay. Thank you.
Any other questions? Okay, thank our speaker again, and we'll turn right over to our second speaker.
Thank you.